objective-minded, the debate is clearly over. The increase of various greenhouse gases in the atmosphere, largely driven by human activities over the past 2 centuries, have created a global energy imbalance which we now know is altering the world's climate. To give perspective to the power of greenhouse gases, at present levels, the world's average surface temperature is 57 degrees Fahrenheit. Without greenhouse gases, Earth would be encased in ice, with an average temperature of -2 degrees. The atmosphere of Venus is composed almost entirely of carbon dioxide, resulting in a constant temperature of 900 degrees. Carbon dioxide has played a very significant role in the current process altering our climate, simply by virtue of the vast quantities released into the atmosphere. Of the more than 60 known greenhouse gases, pound per pound, carbon dioxide is in fact one of the least effective at trapping heat. The impact a greenhouse gas will have on the climate depends on 2 distinct values. First, its relative concentrations in the atmosphere at any given time, and second, its unique molecular capacity to prevent energy from radiating into space. The accuracy with which we measure and apply these 2 values to climate science simply dictates how well we can recognize the cause or anticipate the outcome of events. For better or worse, the laws of physics will determine the actual results. For the sake of convenience, years ago, the scientific community adopted a simplistic method for comparing the climate impacts produced by these various gases, assigning each gas a value known as a global warming potential, or GWP. The definition of a GWP for a particular greenhouse gas is the ratio of heat trapped by 1 unit mass of the greenhouse gas to that of 1 unit mass of carbon dioxide over a specified time period. This simplified method allows a single numerical value for any greenhouse gas to be inserted into research data and computer models for a direct comparison with carbon dioxide or other gases. Throughout the world, climate research is based on the GWP values of greenhouse gases as measured over a 100-year time horizon, commonly known as their carbon dioxide equivalent. At first glance, it might seem logical to compare the impacts produced by all gases over this lengthy time frame. After all, climate science is based on the concept of looking beyond the daily variability of weather, recognizing instead the long-term patterns which define the regional climates we depend upon for food production and other issues. Unfortunately, the GWP system has an Achilles heel. Among the greenhouse gases, methane's ability to oxidize energetically not only makes it a highly efficient fuel, but gives it a relatively short lifespan once in the atmosphere. An emission of methane converts into carbon dioxide and water vapor, rapidly at first, then progressively slower as its molecules are depleted. Including residual climate impacts produced by the resulting water vapor, methane has a total atmospheric lifetime of just 12 years. As updated in the IPCC's 2007 report, when measured over a 100-year time horizon, the global warming potential for methane is 25, meaning that methane is considered to be 25 times as potent a greenhouse gas as carbon dioxide. Not surprisingly, an examination of scientific reports and articles pertaining to methane's climate impact reveals a consistent view of its greenhouse potency at this level. However, as each GWP value simply represents the total climate impact a gas is expected to have when measured over a specified, arbitrarily chosen time period, a comparison of methane's alternative time horizon reference values provides insight into the accuracy achieved by their use to assess the dynamics of methane's impact. To put this in simpler terms, each of these cups represents an equal amount by weight of either methane gas in red or carbon dioxide gas in green. Measured over a 500-year time horizon, it takes this much carbon dioxide to equal the climate impact produced by this much methane. Measured over a 100-year time horizon, the value now used in climate science, 25, is represented in dark green for the sake of distinction. Measured over a 20-year time horizon, measured over a 10-year time horizon, and measured over a 1-year time horizon. If methane's climate impact were simply an academic issue, its molecular efficiency at trapping heat and rate of chemical decay once airborne would be of little concern. However, as methane's emissions can actually trigger even larger emissions, these factors have enormous practical implications. While climate trends have followed scientific projections in general, observations have shown a broad range of discrepancies, including the rates of sea level rise and ice loss from the polar ice sheets and from glaciers at all latitudes, as well as changes to global precipitation and weather patterns. One of the most dramatic failures in climate projections to date regards the annual minimum coverage area of Arctic sea ice over the past few summers. Compared to the range of results from the 18 supercomputer models used for the IPCC's 2007 climate report, the actual minimum extent reached in September 2007 preceded even worst-case projections by 30 years. While scientists have long recognized the Arctic's vulnerability to a warming climate, research and climate models have clearly failed to take into consideration a key factor in projecting rates of change. With the average minimums for 1979 through 2000 outlined and the 2007 record minimum shown, The difference in size is remarkable, equal in area to the states of Texas and Alaska combined. When ice thickness is taken into account, the minimum volume of sea ice in 2007 was only half that of 2003. During the Arctic winter, solar energy is dramatically reduced to a vast region of land surrounding the Arctic Ocean, producing a perpetually frozen landscape known as Arctic tundra, or in general permafrost. As only a thin surface layer is thawed during summer, the organic remains of plants and animals have slowly accumulated into frozen, carbon-rich deposits, sometimes hundreds of feet thick, with a total mass well over 500 billion tons. In recent years, the warming climate has allowed Arctic tundra to thaw in summer to increasing depths, producing carbon dioxide through organic decomposition on dry land, as well as methane gas from the vast areas of lakes produced by melting ice deposits. Before 2007, methane emissions from these Arctic lakes was already approaching 50 million tons per year, with emissions expected to increase exponentially as thawing accelerates through positive feedbacks. In April, new data revealed that in 2007, annual global emissions of methane unexpectedly jumped by 27 million tons. This followed a decade without increases, due in large measure to the Methane to Markets program, aimed at reducing the 60% of global emissions currently resulting from human activities. Scientists consider thawing Arctic tundra a likely source for much of this recent increase. Besides methane's direct warming effect on the Arctic region, increasing concentrations have influenced ocean and atmospheric currents and amplified the impact of changes to the region's albedo, or reflective characteristics. Taken together, these forces have contributed significantly to accelerating sea ice decline, and in turn have awoken a slumbering beast. Frozen within the sediment of the shallow continental shelf along Asia's northeast Arctic coast is a submarine counterpart to the perpetually frozen landscape above. This ancient permafrost layer contains methane molecules trapped in a structure of ice crystals known as hydrate, which remains stable and solid under the extreme pressure and low temperatures found here. With climate projections calling for only a gradual decline in Arctic sea ice over the coming decades, scientists have long considered this permafrost formation of no critical importance, despite its holding 540 billion tons of methane hydrate and capping an additional 360 billion tons of methane gas. However, as the forces of change have increasingly pushed back the reflective shield of the Arctic sea ice in recent summers, a chain reaction commenced. Data from the past year reveals that additional solar energy penetration to the seabed has, in places, raised the temperature to the thawing point. As a result, this normally solid subsea permafrost has now grown porous, producing supersaturation of dissolved methane within regional seawater and sea-level atmospheric concentrations of methane 5 times above normal. With Arctic sea ice conditions primed to set another dramatic record this summer, a critical threshold in the integrity of this permafrost may be fast approaching. Recognized or not, methane's true dynamics have and will continue to play an enormously crucial role in the accelerating cascade of events underway throughout the world. Without a corrected reassessment of critical issues, we will fly blind into a future of unprecedented challenges. With all due respect, I need your assistance to complete this reassessment while options exist. To help, please visit our website now. Thank you for your time.